That's that's my position. I think that, you could, argue if you're religious, you would not say that, right? But I think that as far as we can tell, meaning is a property of consciousness. It comes from thinking. And thinking is something that we do, and we're physical structures. So it's something that emerges from a very complex physical system. The most complex thing we know of anywhere in the universe, which is the human brain. So my argument is that if there are no structures as complex as human brains on any of these other planets in the Milky Way galaxy, then there's likely no meaning there. So it means meaning. I have a friend who was the Dean of Guildford Cathedral, a wonderful man called Victor Stock, who's great, and I had loads of conversations with him. And in the end, we figured out that the only thing we disagreed on was that he thinks meaning is eternal and universal, whereas I think it's local and temporary. I think it comes from us. It's a property of things like us. And I think that it's sort of weird to say that, because it's a scientific way of looking at the world, right? It's just, there's nothing, that's what it is. But it kind of puts us back at the center of the universe in some strange sense, or elevates us, I think. It makes us very valuable because of the rarity of structures like us. So, science has we've spent the last 400 years demoting ourselves from the center of the universe physically and finding that we're physically insignificant. But I also think we've got more and more knowledge about what a remarkable and probably rare thing a human being is. But I think, if you're walking through some forest and you just tread on an orchid, let's say a rare orchid is there, it's just there, and it's just one thing, you tread on it. What's your reaction to that? Is it to say, oh, it doesn't matter, it was going to be gone tomorrow anyway, it's a rare thing, they don't last very long? Or do you think that there's something of immense beauty that should be protected because of its ephemeral nature of its existence? I once visited Frank Drake, actually. So there's a thing called the Drake equation that is very famous. It was Frank Drake in the 50s and 60s, was one of the founders of SETI, the Search for Extraterrestrial Intelligence. And so he had a thing which, can we try and work out how many civilizations there might be in a galaxy? But I went to meet him quite late in his life. He died a few years ago, but it was wonderful at his house. And he collects orchids. And there was an orchid there that we'd arrived, and it blooms for one day a year. And it was just happened to be on the day that we arrived. And he said, this obviously makes it more beautiful. No one could argue that this one that blooms on one day a year is less beautiful than the one that's just always there.
Yeah.
Right? It's a beautiful thing. So we all understand that. But he said, actually, that maybe that's what civilizations are like. So maybe the fact that we haven't seen anyone or heard anyone is just because they're like these little orchids that just flower and then disappear.
Yeah.
But that would make them more beautiful to me. That's what we are. Almost everybody, I would say everybody that I meet, is interested in the questions that are raised. Astronomy and cosmology, but also biology, just science in general. But it's how you phrase the questions. Are we alone in the universe is a question that people think about. Even, are we alone in the solar system? Are there microbes on Mars? But also these bigger questions about, how did the universe begin? Why is there a universe at all? How come there are things like us in the universe, which are just little patterns of atoms that can have a conversation? There's an observation a few weeks ago from the James Webb Space Telescope of a galaxy from which the light had been traveling for 13.5 billion years to reach us. So the universe is 13.8 billion years old. So you're seeing this thing as it was just after the universe began. So you say, well, how did the universe go from that, which is these early galaxies, and even before that, just a load of hydrogen and helium, nothing else? How did it go from that to us? One of my great heroes, Carl Sagan, said that a physicist is a hydrogen atom's way of learning about hydrogen atoms. And you go, that's what a beautiful way of putting what a human being is. We started off as just a load of hydrogen a couple of minutes after the Big Bang, and now we're these things. And that story is quite majestic. I think everybody's interested in that. I mean, it is a remarkable thing to be a human being, and we don't know how far you'd have to go out into the universe to find anything remotely as complicated or wonderful as us. It might be beyond our galaxy you'd have to go. So but that's, as you rightly say, it's a very wide perspective, and it's kind of a luxurious thing to be able to think like that when you're busy every day and you've got real things to do. But I also think that it's almost meditative in a way. So learning about nature, which is what we're talking about, and nature is not just leaves and plants, it's stars and the universe beyond, is kind of quite a diverting and experience, and it's quite a joyful, pleasurable thing to, and ask very simple questions about, for example, why is the grass green is a good question. So you can sit there and look at the grass, and maybe you don't think about it too much. You say, why is it green? And it's green because it does photosynthesis, and so it takes energy from the sun. And you say, why does it do that? And why does it reflect the green light? So we see it as green. And in the end, actually, you'll end up going on a journey that takes you back through the whole history of life on Earth. And so suddenly you start asking questions about, how did the plants come to be on the land? And it was 500 million years ago or something like that. And that ultimately, by asking those little questions, you end up going on journeys in your mind that span billions of years and billions of light years. And so, I think that, obviously I would recommend it. What is life? That's a very good question, by the way. The answer is we don't really know. There's a very famous book in the 40s that sort of predicted the existence of DNA, which was discovered later. A great friend of mine, actually, Sir Paul Nurse, who's got a Nobel Prize, who runs the Francis Crick Institute here, or founded it in London. He wrote a book recently called What is Life, which is brilliant, from a Nobel Prize winning biologist. And he ultimately says that we don't really know, but you can pin some things down. So one, as you said, is it's something that happens. It's that there's energy, a flow. By energy, I mean, what do? We burn food in oxygen. And if we stop burning food in oxygen, then we die. So there's an energy in the way a steam engine does things. So there's that part of it. And then there's information. It processes information as well. So that's what we do. So there's an information component and an energy component. But the point is, it's just at a fundamental level, it's no different to something like a computing device, in the sense that it obeys these basic physical laws, which there's got to be a source of energy, and you've got to be able to do things, and your structure remains and things like that. So that would imply that it's the same as if your iPhone will stop processing information if you take the battery out. So it's dead. It's a dead iPhone. The idea is that and this was all the way back in Schrodinger's book, he said this in the 40s, life obeys the laws of physics. So it is part of the physical universe. And so therefore, you don't have there's no conceivable way that your conscious experience can persist when the machine stops working. And that might sound harsh, but I would flip it around, as we did before, and say, isn't it remarkable that there's this kind of thing? It's just obeying the laws of physics, and the laws of physics are pretty simple. There are only 4 forces of nature, and it all started out as hydrogen and helium 13.8 billion years ago. And we managed to get into these patterns that can genuinely, I really mean it, bring meaning to the universe. Like, let's say you don't like flying, for example. So some people don't like flying, and you get nervous. But you can actually go and look at the data and find out that it's safe compared to other modes of transport. So you could just say, okay, I'm not going to be scared of flying then. If you really can trust the data. So it is useful to look at facts are useful. I know it's difficult, and I know that we all have different, sort of things that worry us for different reasons, and that's part of being human. But you can kind of liberate yourself a bit from it. I did there's a podcast called A Question of Science, and I love it actually. And it's out at the moment. They're coming out once a week, and it's just at the Crick Institute, and it's just experts on a panel, and I chair it, and the audience asks questions. So it's like Question Time, but with people who know what they're talking about. Basically, is the difference. And so we did one for example, can we cure cancer? Because it's mainly a lot of the Crick Institute is cancer research. And it was a tremendously optimistic program, actually, because you realize how rapid the progress is in understanding this disease. And just look at the statistics, as you said earlier, the survival rates. Anyway, so we did cancer, aging, dementia, those things. But also we did one on AI, which was really interesting to me, because the question is, is there any difference between us and a computer, let's say? So could you imagine what they call it AGI, artificial general intelligence, that's like us, rather than just a thing that does one thing at a time, which is what we have now. And there was some debate actually, and the more neuroscience-y people felt no, that it's really very difficult, that the human brain is much, not that there's anything mystical going on, but it's so complicated, and it's all to do with our experience of the world. It's connected to our bodies. So I think the jury's still out on whether we're just, whether we now, in our conversation, whether we could be having this in a big computer. And I think the jury seems to be still out amongst the experts on that. Biology is really difficult to simulate. It's amazing. I'll probably get it wrong now, but someone was telling me at the Crick about some work they've done on mice, and they're looking at how they smell, the olfactory sort of system. And they had these sort of, they just begin to see that there's little co-processors in the brain. So a smell will come in, and this thing will kind of take that data, which is just it's the same data that comes from your eyes or your ears, right? They're all just neurons going in there. So your brain sort of figures out, what is it? It's a smell thing, it's not a sight thing. And then what is it? And then what would that do? Where is it? So it sends some data to a spatial bit of the brain that is dealing with where it is and how far away it is. And then another bit to, is it something you should not like, or like a reflex sort of thing? Or is it something that you use to build your model of the world? So is it telling you there's a forest around the corner? And it's so remarkable that they're just beginning to map out which bits of the brain do this and how they get the data and where they distribute it to. And it was amazing to me, because you're right, we know a lot about it, but we don't know as much as we would like to know. I like scientists that have made a massive contribution that we haven't heard of. So one, which I was lecturing about the other day and talking about, is there's a scientist called Emmy Noether. And Noether, Einstein described as one of the greatest mathematicians in history that many people have never heard of. And Emmy Noether, what she did was she showed the relationship between what we call symmetries of space. So the fact that the laws of nature are the same now and will be the same in 2 seconds' time, right? So that's a symmetry in time. That's related to the conservation of energy. And she showed that the fact that if you do an experiment here and here, then you get the same outcome. The laws of nature are the same, is related to something called the conservation of momentum. It's like the recoil of a rifle and so on. So she's one of my favourite scientists, because not many people have heard of her, but it's massively influential. So the nearest large galaxy, Andromeda, is about 2 million light years away, which means light travelling at 300,000 kilometres per second from our point of view takes 2 million years to travel from the Andromeda galaxy to us. So if you go away from the city lights and out on a clear sky, and when there's no moon particularly, then you'll be able to see Andromeda if you've got some binoculars, and it's worth looking at. Because the light entering your eye began its journey 2 million years ago, which is before we'd evolved on Earth. So that gives you a sense, and you can see that. You can just about see it with the naked eye, because it's big. It's a big galaxy, about 1 trillion stars. And it's actually, although it's very faint, it's bigger than a full moon on the sky, so it's a big thing. I think that's the best explanation of the scale, because you can just about, I think, get your head around that. But that's the nearest galaxy. So when you start talking about galaxies that we see, beautiful images with the Hubble Space Telescope or the JWST, for example, you're looking at things that are 50 million light years away, 300 million light years away for a thing called Stephan's Quintet and onward. And those, 300 million light years. And many of the galaxies we can see in photographs with like the James Webb, for example. Those things are so far away that the light began its journey before the Earth had formed. And that's incomprehensible, I think. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea apparently independently of each other. One was a clergyman, an English clergyman called Mitchell, and the other was the great French mathematician Laplace. And they were both thinking in terms of an idea called escape velocity. So the escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star. For the Earth, for example, the escape velocity from the surface of the Earth is around 8 miles a second, 11 kilometers a second. If you go bigger, you make a bigger, more massive thing, let's go up to a star, for example, like the Sun, then the escape velocity increases because the gravitational pull at the surface increases. And actually for the Sun, it's somewhere in the region of 400 miles a second. It's really fast. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is they imagined in their mind's eye, well, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? And then you wouldn't be able to see them. There's a wonderful quote, actually, in Laplace's paper, where he says that the largest objects in the universe may go unseen by reason of their magnitude. And this is back in the 1780s or 1790s. So he's imagining stars where the gravitational pull is so vast that even light can't escape and you couldn't see it. Dark stars, I think he referred to them as. Now we know that such objects do not exist in the universe in that sense, in the sense that Mitchell and Laplace meant. But actually, they missed something, which is not surprising because it sounds almost paradoxical. But you can also increase the escape velocity of the surface of an object by squashing it. And it turns out that if you take the Earth and you squash it down and squash it down and squash it down until it's about that big, the radius just less than a centimetre, then the gravitational pull at the surface would be so great that light couldn't escape. And that is essentially the modern concept of a black hole. Now, Mitchell and Laplace's calculations or imaginings were based on Newtonian physics, so pre-Einstein. We come forward to 1915, Einstein published his general theory of relativity, which is a different model, a better theory of gravity. And it turns out that black holes also exist in general relativity. Now, if we come forward to 1915, Newton's theory of gravity is replaced by a better model, a better theory, which is Einstein's general theory of relativity. But the idea that there can be objects that can be compressed such that they trap light is also present in Einstein's theory. The first physicist to predict such a thing, or at least derive the mathematics that describes such a thing as a black hole, although he didn't know that they existed, was a man called Karl Schwarzschild. What Schwarzschild did was provide an exact solution to Einstein's equations that describes space and time, the distortion of space and time in the region of a star, or at least an idealized star, which is a perfectly spherical, non-spinning ball of matter. It's a simple model of a star. Now, Schwarzschild described or discovered the solutions to Einstein's equations that describes what happens to space-time outside such a thing way back, actually 1916, just after the theory was published. What Schwarzschild's solution also describes, though, although he didn't think in these terms at the time, was what that space looks like if you completely remove the star, but leave its imprint in the fabric of the universe behind. And that is essentially the theoretical description or the model of a modern relativistic black hole. Now, while Schwarzschild's solution, and by solution I mean we're to picture a distortion in space and time, a distortion in the fabric of the universe. While Schwarzschild's solution does indeed describe the simplest possible black hole that we can model in the universe, people didn't really think in those terms at all until later. You see in the 1930s, Einstein and a colleague of his, Rosen, for example, exploring that space-time and building models of what that space-time might look like. But I think it's true to say that really, certainly until the late 1930s, and actually arguably post-war until the 1960s, most physicists thought that such things would not exist in nature, so they were theoretically interesting, perhaps not practically interesting. The reason is that you have to create such a thing. So it's one thing to have a model of space and time that describes this object called a black hole, from which not even light can escape. But it's another thing for nature to actually make it. So if you go through the 1930s, there's a lot of papers. Actually, Robert Oppenheimer and a student of his, Snyder, wrote a very famous paper just before the war, which explored whether a real star in the universe at the end of its life could collapse and collapse without limit to form this geometry, this thing that we call a black hole. Just before the war, Oppenheimer and Snyder showed that under certain assumptions, a star could behave in such a way. But it wasn't really until the work of people like Roger Penrose and Stephen Hawking and several others in the 1960s that it really began to look as if nature would build these things. There's this great quote I remember with some fondness, actually. Arthur Eddington, a colleague of Einstein's, who was very English, very proper physicist, and he said, "Nature will prevent such absurdities from existing." That's it. Nature will prevent it. Well, it turns out nature doesn't prevent it. We now know, and we've observed them, that stars do collapse to form black holes. And then theoretical physics moves on. So people accept that these things should exist. Although it's true to say that we haven't actually imaged one until the 21st century. But in any case, people accepted these things should exist. More and more evidence mounted that they do exist at the centres of galaxies and at the sites of collapsed stars. But then we have to face the consequences. What does it mean for our understanding of the universe if there are these objects where space and time behave in a very strange way, where light is trapped, and where it would seem that anything that falls in is at the very least locked away from the universe forever? So to understand the conceptual problems that are faced if these things exist, then it might be worth just describing very briefly the Einsteinian description, the pure description in general relativity. A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description, It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. But we'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly. Slower and slower and slower as the astronaut approached the black hole, until on the horizon you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now, just in Einstein's general theory of relativity, actually, it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called the singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not, and is still not, understood. So that's a great mystery, and it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are, we have a problem with the singularity, we don't really have any access to it, we don't have the conceptual tools to explore it, so it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole. Not in this extreme place, not only in this extreme place, at the singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important. In 1955, actually, one of the great physicists, Richard Feynman, wrote an essay called The Value of Science. And so what is the value of this? So it's obvious that we wouldn't have an iPhone, you wouldn't have modern medicine, you wouldn't have all those things, right? That's obvious stuff. But actually, it's because you're trying to understand nature, and the amount of knowledge we have is changing all the time. And so the picture we have of how things work and the theories and our understanding changes all the time. You get used to the fact that you're often wrong. So as a scientist, you're almost always wrong, actually. If you're doing a PhD or something like that, you go, I think it works like this, and nature will say no. And you go, okay. But so you learn to be delighted, actually, when your opinion turns out to be incorrect. That is a skill that I think we can all agree that many people in public life and elsewhere have lost. But of course, if you're not comfortable with uncertainty and comfortable with being on the edge of the known, then you never learn. And Feynman, actually, in this beautiful essay, I strongly recommend it. You can download it from anywhere. It's Richard Feynman, The Value of Science. It's about 4 pages. And he says in there that even if you think about what democracy is the admission, fundamentally, that you don't know how to run a country. Because you accept that you change the government every 4 or 5 years. And that's a positive thing. So the moment you see someone saying, this is the way to do it, then you know that is not the right person for the job. They're not actually a Democrat, because democracy requires you to think that you're flawed and your understanding improves and you get most things wrong, but sometimes you get something right. And that's how we make progress. And that's what science is. So there would be no modern medicine without that process. And it's interesting that Feynman also, he works on the atom bomb. He works on the Manhattan Project. So it's not surprising that in the 50s, he was thinking about this stuff, because he thought he'd delivered the power to destroy ourselves. He had delivered us the power to destroy ourselves. And the other, more famously, Robert Oppenheimer. So everybody knows Oppenheimer, especially because of the brilliant film. So Oppenheimer wrote about the same things in the 50s. And again, he was writing about this idea that you have to embrace doubt and not fear doubt, but embrace it. And also, actually, Oppenheimer, he gave the BBC Reith lectures, really famous lectures in the 50s. He was 53. And he said, there's a wonderful thing I remember where he said that everyone, to be a person of integrity, to a thoughtful person, you'll have an anchor. So you'll have beliefs, and you'll have a framework and a moral framework, and you'll believe things. And that's really important. To be a person of substance, you have to have a position. But the key is to realize other people have different anchors. And so we all have our different anchors. And the challenge on this planet is to make sure that we work together in the interests of the planet as a whole and the civilization. And that sounds like a bit hippie maybe and whatever. But actually, if you think about it, if you're the person who built the atom bomb and you saw 2 of them dropped on Japan, and so you know what the power of those weapons is. One of the things you might think about is how to not do that. And they're worth reading, these people, because I think in some ways we've forgotten it. I think it all comes back to what we were talking about earlier, that we've not figured out how to run a world, definitely. And we've sort of figured out how to run societies, but maybe we're not doing a very good job at the moment. And I would guess it's something to do with the rate of change and I suppose social media and things have fed into that, and we're having to live in a different way and interact with people in a different way, and we've not adapted. But I think it's the number one challenge that we face, for all the reasons we've spoken about, how valuable this society is. One of the possible explanations for why we don't see any other civilizations out there is because they don't get very far. So if you think about us at the moment, it's only in the last century, half a century, that we've had the power to destroy ourselves. And we've managed to avoid it. It's remarkable, probably, that for 70 years or so, since the invention of the atomic bomb, we haven't used them again. But we might do. And maybe there's a theory that essentially says it's too difficult to manage a planet. So when you have so many billion living things, people in this case, on the planet, you just can't get along. So I would hate that to be the case, because I think that we're so valuable and so rare. But we don't really, the progress we've made seems to be unraveling somewhat at the moment. The worst place for us, almost all of it, actually, beyond Earth, is horrible for us. It's almost like where is somewhere that isn't scary, because we couldn't exist. We couldn't exist anywhere unprotected, anywhere from about 35,000 feet upwards or less, right, from the top of Everest upwards. We could, and then if you go underneath the water, right. So for us, if you go just a little bit down in the earth or a little bit up, there's a narrow band which is not scary for us, and everywhere else is horrible. Amongst the worst places are the sun, right? The sun's really not very nice. No, all of it is all absolutely terrible. Prove that the moon landings are real. You just look at any photograph taken by modern spacecraft, for example, which are not American spacecraft, if you want to be really conspiratorial about it. We have photographs of the landing sites with the stuff there. And I've met several of the people that walked on the moon. I've been very lucky to do so. And they are undoubtedly not bullshitters. And you've seen the video of Buzz Aldrin punching someone who said otherwise, and I fully supported him in that endeavour. How many galaxies are there? In the bit we can see of the universe, let's say 1 trillion. And you'll see different numbers, because it's hard to measure, actually. So we're making estimates based on little bits of the sky that we can observe. It's billions and billions and billions, to paraphrase Carl Sagan. And it's something like, you could say 300 billion, 500 billion, 1 trillion, even 2 trillion. So within a factor of 2, 3 or 4, we're not really sure. It's an estimate, because you can't count them. It's an exercise for everybody who's listening. Count to 1 trillion and then come back to me when you've done it. That's a lot, right? I'll get it slightly wrong. There's a great scientist called John Wheeler, who's one of the most famous physicists of the 20th century. And he said that we live on this little island of knowledge surrounded by an ocean of ignorance. But as the size of our island of knowledge increases, so do the shores of our ignorance. And actually, the live show that I'm doing now, it starts with a story about a scientist called Johannes Kepler. So Kepler was working in the early 1600s, And he's famous for the laws of planetary motion. So in a way that I cannot conceive how he did it, just from watching the planets like Mars and Jupiter and Saturn, which was some other astronomers had catalogued where they are in the sky, which we've known for thousands of years. It's astrology, right? Where the planets are against the stars. So he took that data and figured out that planets go in ellipses around the sun. And he figured out a relationship between how long their year is and how far away from the sun they are. It's remarkable just from this data. But he was really clever. And in 1609, there's a beautiful story that he wrote about where he was walking across the Charles Bridge in Prague in a snowstorm. And it was snowing and it was New Year's Eve, as he tells it. And he was going to his benefactor's house to a party. So he was going over the New Year's Eve party to the guy that pays him, and he realised he hadn't brought him a present. And so he noticed the snowflakes landed on his arm, and he looked at them and he said, "Why are they all six-sided? Right? They're all different and really beautiful, but they're all six-sided. So what is it about that?" So he wrote this book going, "Why?" And he said, "Well, they come from water, so maybe there's something in the water. Maybe it's what the water's made of that makes the snowflake," which is right. He didn't know, it was 1600. And maybe so something to do with that. Maybe he didn't know about molecules, but he makes all this progress, and he talks about beehives and pomegranate seeds and everything that's got these geometric shapes. And he's on the right track. We now know it's the water molecule, and we know about that, but it's a 20th century discovery. But right at the end, after he's written this wonderful book, which you can just buy, I recommend it, it's called The Six-Cornered Snowflake. Right at the end, he just says, I can't go any further with what I know. And he says, "I leave it to you, dear reader, to the people of the future." The translation I have, he says, "I'm knocking on the doors of chemistry." We didn't have chemistry. We didn't know anything. But you see this brilliant mind asking all these questions and then almost being happy at the end, going, "Oh, it's great, it's something for the people of the future." And this is one of the greatest minds, I would say, the Kepler. I mean, he was a genius. But you're right, he's asking this really childlike question, which is a very deep question. And actually, someone wrote recently, it was a Nobel Prize winner, I've forgotten who it was, but he was asked, like, what if you were to go to kids to school and say everything's made of atoms, things are made of atoms, is there anything you can do as an experiment in a school to show that? It's very difficult. And he said it's probably the shapes of things like snowflakes, because if you see something, and Kepler said, I cannot believe that this beautiful shape exists at random. There's a reason, and the reason is the water molecule. And you have to know quantum mechanics and all sorts of things to understand why the water molecule is the way that it is. But that idea that crystal structure like a snowflake is telling you something about a deeper picture is a really modern way of looking at it, and it's right, it's correct. So it's probably snowflakes. Snowflakes are probably the example. There's something that's telling you there's something else going on. The snowflakes, so they're all six-sided, but then you say, well, why are they all different then? Which Kepler also noticed. They're all different, but they're all kind of similar. They're all different because they have different formation histories. So it's the path they take through the clouds when they form that gives them their shape. That's true of us. So we're shaped by the path we take through life. But in terms of the thing about destiny, so it has a name in science called teleology, which is the idea that there's the cause is in the future. So you're evolving towards something. And that's not the way that we think of the universe scientifically. So evolution, for example, like why are we the way that we are? It's all about our evolutionary history. We're not evolving to become smarter or something like that. You evolve to fit your environment, but it's not that we're not some kind of ascent to some grander form. That's not the way that we think in science. I'm not sure if we're getting smarter. I mean, when you look at even recently people like Kepler, If you read that book, you see a modern mind, a very, very clever person. So I don't think we've got smarter in the last few hundred years. In fact, in the past few thousand years, no one's got smarter. The really interesting question is what happened to civilization and society that allowed us in about 1600 to suddenly start basically doing science, which has led to the modern world. Because if you think about it, without being dismissive to everyone who lived before that, we didn't make much progress, right? Yeah, if someone from ancient Greece went back 2,000 years to ancient Egypt, they wouldn't really notice a lot different. But it'd be a bit different. They'd have pyramids rather than temples. But it basically, the knowledge they had about the world hadn't changed. So it didn't change ever, basically, thousands and thousands and thousands of years. And then around 1500, 1600, suddenly we start accumulating knowledge. And in only 400 years from Kepler, thinking about these points of light, we've visited them all. 400 years. We've been to every planet that Kepler saw and discovered some that he didn't know about. And now we have a spacecraft, the Voyager 1, it's 50 years since it was launched. It's on the edge of the solar system. It's on the way to the stars. And that happened in 400 years. So I find it really interesting that it's not people have got smarter, it's that our society got smarter. So if you look at the way our civilization works, a large amount of the things we take for granted are delivered from space. So there's a number, I think there was a report from the Royal Society, which is the UK's oldest scientific society, about a year ago. And I think the number is 16% of UK GDP. It's a very big number. And because if you think about it, we use it for all our communications, we use it for the timing of our computer networks, financial transactions, weather forecasting, understanding climate and all that kind. So the list goes on and on. Already we're talking about that there's experiments to manufacture drugs and medicines, as you say, on the space station. Some things are better manufactured in zero G and so on. But even now, it's so integrated with our society that if we lost that infrastructure, it would literally, the civilization would grind to a halt. So we're already completely entwined with it. And I think so we make a mistake when we think of space as science fiction. It's really not. It's part of, I had a discussion with someone the other day, and they said, you shouldn't think of we talk about the space economy, which is growing. And we're thinking about things like mining asteroids and putting power stations in space and so on. And then the Earth economy. But they said, no, it's just the economy. It's all the same. We're expanding outwards. We're already, near Earth orbit is completely entwined with everything that we do. It's becoming very important to manage it as well and to regulate it, to make sure it's not the Wild West up there, because it's essential to all our lives. I mean, asteroids, so there's the resources. There's an argument, which a lot of the people, the early sort of evangelists for space, there's a guy called Gerard O'Neill, later a guy called Robert Zubrin, who influenced Elon Musk quite heavily. And they all had this view that we're putting too much pressure on the planet, obviously, which I think everyone agrees upon, about resource extraction and so on. But the thing is that there are resources, an infinite amount of resources up there above our heads, if we can access them. And a lot of the early sort of pioneers and thinkers felt that would relieve the pressure on Earth. And it would, in principle, if you can do it. It relieve the pressure on Earth because you're not fighting over resources on Earth. You've realised that you can just go to that asteroid, the moon, Mars, and so on. And it often sounds like, as I said before, it sounds like science fiction and naive. And it maybe was in the 70s, maybe it was rather sort of wishful thinking, but it sort of isn't now. And so I think there are great benefits to be had from moving into space. And it gets a bad name sometimes because we all know about the controversies around people who go there and space tourism and all those things, which would be fun. I'd quite like to do it, but obviously it's whatever. But actually, the real potential there is to allow us to expand as a civilization without damaging the planet. The modern revolution in our thought, which is still ongoing, by the way, in understanding black holes and quantum gravity, really does begin with work that Stephen Hawking did in the mid-1970s. Stephen Hawking, in his own words, showed that black holes ain't so black. So we've described them as prisons, in a sense. We're picturing them as a region of space from which nothing can escape. What Stephen Hawking showed in a landmark couple of papers, a tour de force of calculation actually, is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow. They produce particles. They have a temperature. This thing that we pictured in Einstein's theory as pure geometry, as just distorted space and time, actually emits particles. It's called Hawking radiation. And one way to picture that, and Stephen in his 1974 paper gives this, he says it's a hand-wavy description. So it's not a full description, you need the mathematics for that, but he gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to imagine, to zoom in on space in the vicinity of the event horizon of a black hole. If you zoom in on any piece of space, the piece of space in front of your nose right now, if you could zoom in and slow time down with a big microscope, you can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. So it's a picture of what the vacuum of space looks like. Just to emphasize again, it's not a complete picture, it's not supposed to be precise, but it's a reasonable model of what's happening. So particles in and out of existence all the time. And that's happening everywhere. In space, everywhere that you look, in the most empty piece of space you could imagine, that's what's happening. In the vicinity of the horizon of a black hole, you can have the situation where one of those particles, those pairs of particles, is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe. It's essentially made real by the presence of the black hole. So the other partner is interior to the black hole, and this particle heads off into the universe, removing energy from the black hole as it goes. And this rain of particles, this glow of particles, is called Hawking radiation. That has profound implications. So it's kind of a simple picture of what's happening. But the upshot is, imagine this thing. It's a black hole, it's glowing, it's just space-time geometry, but it's emitting particles, losing energy, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons, they have a lifetime. One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, a region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation. Those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true? Or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Let's say that I take anything in here, in this room, a book, a table, the camera, right? Anything at all. And I set fire to it. I incinerate it. I destroy it in any way that I can. I could throw it into a furnace. I could put it in the heart of a nuclear bomb and explode it, right? Whatever, just completely incinerate it. In physics, in basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, and I was clever enough, then I could reconstruct the thing that I had destroyed. Information is conserved in the universe, as far as we know. So every law of nature that we have says that information is conserved. The problem was that Stephen Hawking's initial calculation of the way those black holes evaporate away said that information is not conserved. Said that black holes are erasers of information. To put it very bluntly, the calculation said that once that black hole had gone, then even in principle, there is absolutely no way you could learn anything, reconstruct anything about the things that fell in, including the star that collapsed to form it. So information erasers, the only information erasers that we know of in nature. That was the initial picture of black holes as Stephen Hawking understood them back in the 1970s and 1980s. This became known as the black hole information paradox. Is there life on Mars? Don't know, but it's certainly possible. And as we speak, we have several missions out there, but one of them is called Perseverance, which is a rover. It's on the surface of Mars. It's taking samples. It's taken a lot of samples below the ground, and they're being packaged up for return to Earth in something that's called Mars Sample Return, because we think that it's possible that life existed on Mars or may still exist, because the conditions were right. It's certainly true that 4 billion years ago, almost certainly Mars is like Earth. When life began on Earth, Mars was pretty much the same, with oceans and an atmosphere and so on. So it's entirely possible. And it would almost be surprising if it hadn't existed, because then it would tell us that even given the right conditions, then maybe there isn't a high probability that life begins or geology becomes biology or whatever the origin of life is. Would teleportation work? It does. So it's been done with photons, for example, so particles of light. So you can do the experiment where you essentially, it's based on having two photons that are entangled, quantum entangled together. The best way to describe that in about a second is that they behave as a single system, basically, but you can separate them. And then you can arrange for another one to come in, so it kind of interacts with this one, such that it ends up, this one over here, which could be a light year over there, ends up being in the same photon, essentially, as the one that came in, or in the same quantum state. So it's teleportation. And the incoming one gets destroyed in that process, or its state is changed. So yes, we do quantum teleportation in the lab, so it's real. The question then becomes, how big an object can you teleport? And I think in principle, there's no reason why you can't teleport anything, right? But it's very much in principle. But yeah, it's right. In the context of science, you make an argument. I think in other disciplines as well, you talk about making an argument. not having an argument, but making one, which is laying out a position. And that's what science is, What is a theory, a scientific theory? It's basically a guess. So you guess. Einstein guessed about the nature of gravity, and it looks like he was pretty close and that theory ended up suggesting there may be an origin to the universe. But we still don't think it's complete and completely right. So that's the process. So you make a guess, and then you'd make an argument, and then in that sense, and then you'd test it. And so you do some experiments and you'd see. And really, what you're doing is not looking for confirmation of your guess. You're looking for the thing where it's frayed, where it starts to not give the right answer, because there's the place to go next. And you're right, what you said earlier, it was interesting about ego, because I think if you really are, if you're a scientist and you really are a good scientist, what you're interested in is finding out how nature works. You're not interested in being seen to be right. And that's the difference, I think. And of course, I'm not naive enough, and I'm not suggesting that scientists don't have egos. They do. There's all sorts of politics. Now, I mean, the Nobel Prizes were awarded today. Everyone wants a Nobel Prize and people feel really good about it. But ultimately, most scientists I've met are pure in the sense they just want to find out how things work. One of my heroes is Carl Sagan. And so he did a great series called Cosmos when I was growing up. But he wrote a book called The Demon-Haunted World, Science as a Candle in the Dark. And I strongly recommend it. And a beautiful book. But right at the start, he tells this story of getting in a taxi in New York. And the taxi driver was like, "You're the astronomer off TV, aren't you?" And he's like, "Yeah." And so he said, "What about aliens? Do you think the UFOs have landed?" And so Sagan said, "No, I don't." He said, "Well, what about Atlantis? Do you think there used to be a city under the sea?" And Sagan said, "No," and whatever. "And what about horoscopes and things?" And said, "No." But Sagan, he was really wise, I think, because he said he didn't think he is a person who's just asking silly questions. He thought he is a curious person who's really interested. And really, he just hasn't been served well by society, by education, because there are answers to some of these questions. And the real universe is infinitely more wonderful than imagined civilizations beneath the waves and things. It's far more interesting than that. But he hadn't had access to the information. And I think that's a really important thing to remember, that there aren't silly questions. There's people being curious. And if they don't know the answer, how did the universe begin is a very good question. And actually, we don't know. We know it was very hot and dense 13.8 billion years ago, but we don't know what happened before that, if there was a before. And so I think that it's really important to, as you said, the curiosity is the important bit. And then it comes down to, it's part of the responsibility of a society to give people the tools to satisfy their curiosity and investigate their questions. What is a wormhole? Are they just science fiction? So, no. The first time they came into physics was in 1930, I think it's 1935, in a paper by Einstein and Rosen. So they noticed that the description of the distortion of space-time in the vicinity of a star, which was discovered by Carl Schwarzschild in 1916, they discovered that if you take that description and you allow the star to collapse essentially into a black hole, and then you extend it infinitely into the past. So you say, well, let's imagine this black hole had always existed. So this universe in which this thing exists is an eternal universe. Then you get a wormhole. So a wormhole, the description of it is in the mathematics that Carl Schwarzschild discovered in 1916 for the distortion of space-time around a star. Literally, you have two universes and they're linked by a wormhole. So one of them is a black hole and the other bit is a white hole. So that's what a wormhole is in Einstein's theory. That requires this black hole to have existed forever. So, and by the way, if the black hole's spinning, then you kind of get an infinite tower of wormholes. So the so-called Kerr black hole, this was discovered in the 1960s by Roy Kerr for a spinning black hole. The solution to that, if it's this eternal solution, is that you have an infinite number of universes connected inside the black hole by an infinite number of wormholes. So the modern work on trying to understand what happens to things that fall into black holes might suggest that there's a kind of a wormhole that connects the interior of the black hole to the exterior universe. And so the singularity looks like this kind of network, tangled web of wormholes of some description. I hedge my language because the language isn't really known yet, but it's one of the ideas, one of the possibilities suggested by the mathematics for the interior of a black hole. And the other thing, the final thing to say, is that you might have heard about, there's something called ER equals EPR. So that's Einstein-Rosen, which is wormholes, equals EPR, which is Einstein-Podolsky and Rosen. EPR was a question about quantum mechanics and what Einstein calls spooky action at a distance, where you can have entangled quantum particles, and somehow it seems that if you do something to this one, in a very real sense, this one's affected by it, but not in a way that you can transmit information, but it's quantum entanglement. And there is a picture where you can picture that as the two particles being connected by wormholes, and that was suggested by Leonard Susskind and others a few years ago. That's called ER equals EPR. So wormholes are on the agenda in trying to understand what space and time are and how they behave. So they're not just science fiction. Would you like to be cryogenically frozen to experience the future? No, I think. I mean, first of all, we don't know how to do it, and we don't know if it's even possible to do. So you'd probably not survive. If I wouldn't do it now. I wouldn't say, well, this is great, freeze my head. If you're thinking of doing that, then don't, because we don't think it's going to work. But at the moment, but if it became possible, it's kind of interesting, isn't it? Because I could ask you the question, because it would mean that you essentially stop living now. So everybody that you know and everything that you know about is gone forever, and then you wake up like 500 years in the future. The area that I work in a bit in research is black holes. And I still think it's mind-blowing that according to Einstein's theory alone, time ends inside a black hole. So the singularity is correctly thought of as a moment in time and the end of time. Whether that's the case is it depends on understanding of quantum gravity that we don't have. The fact that black holes exist, I think that gravitationally completely collapsed objects that distort space and time so much that even light can't escape once it crosses into the interior of the black hole, if indeed the black hole has an interior. We're even arguing about that these days. So I think black holes exist is my favourite fact. It's interesting, these objects which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape. Predictions that such objects existed go all the way back to the beginnings of relativity, back at the turn of the 20th century. But actually, really, I would say into the 1960s, perhaps even into the 1980s, many physicists felt that because of the intellectual challenges that these predicted objects pose, many physicists felt that maybe nature would not create them. I even saw the great physicist Steven Weinberg say that he, in some sense, hoped that these things would not exist because they're so confusing. But we now know that they do exist, and so we have to face the challenges that they pose. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper theory. The thing to say, and this always has to be said, you're right, at the same time as talking about the potential of space, is that this planet is the only one that we can live on in large numbers in the way that we do. It's perfect for us because we evolved on it. So it is the best place in the universe by far to be a human. And that's just a statement of fact. So yes, we can build colonies on Mars and the moon first probably. And there'll be a few hundred people or maybe a few thousand people, but it'll be horrible. It might have some nice greenhouses and some big sort of buildings, but imagine living your life confined to a building. There are not going to be rivers on the surface of Mars anytime soon, if at all. Even if you can terraform the planet in hundreds of years' time, it's just not nice. So we have to remember that as a human being, this is the best planet in the universe because we evolved on it, and there will not be a replacement. How many civilizations are there in a galaxy like the Milky Way? Or specifically in the Milky Way galaxy? And the answer is we don't know. So it's a big galaxy, 400 billion stars. Most of them have planets, so there'll be trillions of planets. There's an estimate that there might be over 10 billion potentially Earth-like worlds in the Milky Way galaxy. So there's a lot of places where life could begin and evolve. But on this planet, it took 4 billion years roughly to go from the origin of life to us. And 4 billion years is a third of the age of the universe. And so many people I speak to make the argument that that might be unusual. It might be microbes on Mars and all over the place. But if that's what it usually takes, which is what it took here to get things like us, there's probably very few planets which have been stable enough to allow life to live on them for 4 billion years. So what I said at that climate summit was, to the world leaders, was, let's imagine that we're the only civilization in the Milky Way galaxy. Just a working hypothesis. Might not be, but might be. So let's imagine that we are. And let's imagine that you, being the leaders, through deliberate action, which would be something like nuclear war, or inaction, like, failing to address the climate crisis or whatever it is, you cause this civilization to be damaged or even removed from the Earth. If you do that, then each of you may be personally responsible for destroying meaning in a galaxy of 400 billion suns, potentially forever. Have a nice meeting. So quantum mechanics is the base theory, we think. I think people tend to think of quantum mechanics as something that applies to atoms and electrons and particles, but not to us. And that's not right. So quantum mechanics is the theory that describes everything. The point is, though, it produces, when you look at big things, it produces behavior which can be more accurately or more usefully, not more accurately, but more usefully described by things like Newton's laws. It is necessary to understand quantum mechanics to understand how a laser works, or how, of course, a nuclear reactor works, or the sun works. So it's not just a theory that's a theory of little things bouncing around. It's a theory that's necessary to understand a lot of things that we take for granted today. And it's an unusual theory. It's strange because it's got probabilities in it. And it was Ernest Rutherford, famously got the Nobel Prize at Manchester for discovering the atomic nucleus. But he pointed out that in the late 1800s, early 1900s, when we start looking at radioactivity, you see that radioactive decay is a probabilistic process. So it means that given something like a uranium nucleus, you can't tell, even if you made 100 uranium nuclei at the same time, you could just make them, then you can't predict when any one of them is going to decay away and emit some radiation. Basically, it's probabilistic. And so that idea was shocking to people, that it appears that the world is not like Newtonian clockwork. So I would say quantum mechanics, my explanation is it's a weird theory, it's a kind of probability theory, but it's the way that things actually are. Here in the UK, the big shows are in October and November next year. So they're the O2 and the arenas in Manchester and Birmingham, Nottingham and things like that. And it's wonderful that it's basically cosmology. It's astronomy and cosmology, but it's kind of like prog rock as well in a sense. Because we've got the biggest possible screens fit in those places, which is at the moment. So we've got things like the James Webb Space Telescope, which wasn't active last time that I toured. And almost every day you see beautiful images, like ultra high resolution, magnificent images of sort of exploding stars and colliding galaxies, just beautiful. And so putting those on those screens is really exciting to me. I was involved in a discussion yesterday, actually. It was really interesting. And one of the experts in the space economy said to me that really we shouldn't think of the space economy as space. We should think of it as the economy, because it's not far. Right? It's just 100 miles up there. So it's about we're in London now, so it's about the distance from London to Birmingham. If you go from London to Birmingham, but you go that way, you end up somewhere where you can do stuff that is useful, and it can produce economic growth. It can produce things like interesting drugs, for example, medicines and things which are not easy to build on Earth and so on. So you should think of space now not as a thing, a separate thing, but as a place where there's an opportunity to do stuff that benefits us all here on Earth, and that's the challenge. Which physics conspiracy theory really riled me up, or you up? I think it is the flat Earth, because it's just bizarre. The moon landing stuff is bizarre enough, but the flat Earth thing requires almost everybody who's sensible in the world to be part of a conspiracy, and just a small number of people who, in my view, appear to be a bit odd, to be the only people who know the truth. So the idea that everybody who's kind of flies a plane or does science or does anything at all is like we've all the clever people have got together to invent something that for no reason at all is just, I don't know why that would be the case. That's my position. I think that, you could, argue if you're religious, you would not say that, right? But I think that as far as we can tell, meaning is a property of consciousness. It comes from thinking. And thinking is something that we do, and we're physical structures. So it's something that emerges from a very complex physical system, the most complex thing we know of anywhere in the universe, which is the human brain. So my argument is that if there are no structures as complex as human brains on any of these other planets in the Milky Way galaxy, then there's likely no meaning there. So it means meaning. I have a friend who was the Dean of Guildford Cathedral, a wonderful man called Victor Stock, who's great, and I had loads of conversations with him, and in the end we figured out that the only thing we disagreed on was that he thinks meaning is eternal and universal, whereas I think it's local and temporary. I think it comes from us. It's a property of things like us. And I think that it's sort of weird to say that, because it's a scientific way of looking at the world, right? It's just, there's nothing, that's what it is. But it kind of puts us back at the center of the universe in some strange sense, or elevates us, I think. It makes us very valuable because of the rarity of structures like us. So, I mean, science has we've spent the last 400 years demoting ourselves from the center of the universe physically and finding that we're physically insignificant. But I also think we've got more and more knowledge about what a remarkable and probably rare thing a human being is. But I think, if you're walking through some forest and you just tread on an orchid, let's say a rare orchid is there, and it's just there, and it's just one thing, and you tread on it. What's your reaction to that? Is it to say, oh, it doesn't matter, it was going to be gone tomorrow anyway, it's a rare thing, they don't last very long? Or do you think that there's something of immense beauty that should be protected because of its ephemeral nature of its existence? I once visited Frank Drake, actually. So there's a thing called the Drake equation that is very famous. It was Frank Drake in the 50s and 60s, was one of the founders of SETI, the Search for Extraterrestrial Intelligence. And so he had a thing which, can we try and work out how many civilizations there might be in a galaxy? But I went to meet him quite late in his life. He died a few years ago, but it was wonderful at his house. And he collects orchids. And there was an orchid there that we'd arrived, and it blooms for one day a year. And it was just happened to be on the day that we arrived. And he said, this obviously makes it more beautiful. No one could argue that this one that blooms on one day a year is less beautiful than the one that's just always there, right? It's a beautiful thing. So we all understand that. But he said, actually, that maybe that's what civilizations are like. So maybe the fact that we haven't seen anyone or heard anyone is just because they're like these little orchids that just flower and then disappear.
Yeah.
But that would make them more beautiful to me. That's what we are.